So, who cares, right? We talk about radioactive waste and what's in it for you. Study goal number 39 says, what does this have to do with the humans? Um, I need to give you some conceptual background first. Um, it's important to know that there's radioactivity everywhere. You're radioactive, I'm radioactive. Because it's just atoms falling apart, you probably have a couple atoms that are falling apart. So do I. The screen I'm talking to has a few more. If you go out into the sun, there's a little bit of energy coming from the sun that can make your atoms fall apart. And so the idea that atoms fall apart shouldn't be that scary. And that's usually not a big deal. We'll get to when it becomes a big deal in a minute. Remember that radioactivity can be energy. So energy can break chemical bonds or break atoms in your body. But skin's a pretty good shield for that. Remember that radioactive stuff can get into your diet or into your lungs. You can breathe it or you can eat it. And now that you have radioactive stuff on the inside, same thing, that can break bonds or break atoms in your body. But if it's on the inside of your body, that's more likely to hit you because you have less skin on the inside. But who cares? This is a very repetitive explanation, but listen carefully. If an atom in your body breaks, so what? Most individual chemicals in your body don't necessarily have a big impact. Inside of a muscle cell, one of the hydrogens in a water molecule gets a little heavy, who cares? One of the oxygens loses a neutron or even a proton, and who cares? Like, that molecule wouldn't necessarily have an impact on you because most individual atoms aren't mission critical. Most chemicals aren't that important. If they were important and you lose a cell, who cares? Your body digests and makes new cells all the time by the billions. So most atoms aren't important, most chemicals aren't important, most cells aren't important. So even if the atom was important, and even if it was in an important chemical, and even if that chemical was in an important cell, you could just shed the cell. Your body does this all the time. Because other mistakes happen, you deal with radioactivity all the time. But here's the if and the if and the if and the if, okay? If the radioactivity happens to get into your body, which is pretty rare, and it happens to affect a chemical, and man, I'm really blowing it, happens to affect an atom, and if that atom changes in a way that affects its behavior in a chemical compound that actually matters, and it starts to do something that affects a cell that matters in a cell system, like an organ that really matters, that can start to affect your well-being. And what we're really worried about with radioactivity is DNA. If you mess with an atom that messes up the function of DNA, most of the time that cell would just get recycled. But what if that cell gets stuck growing? We call that cancer. And if it starts to make a whole bunch of cells that get stuck growing, we call that a tumor. And most tumors don't matter, but if that tumor affects your body's functions, then you could have a harmful tumor, and that could be really scary and difficult to deal with. So all energy can mess up chemistry, but what we're really worried about is the stuff over here, the ionizing energy. So a little bit of ultraviolet like you get from tanning beds, x-rays like you get from medical x-rays, and gamma radiation. That's super high energy. That's really scary. Gamma radiation is super high energy. That can go right through your body. It goes through water. It goes through metal, concrete. One of the only absorbers is lead. Remember, there's a lot of ways to get this into your body, but gamma radiation we really, really worry about. People who work in nuclear power tend to have higher exposure than everybody else. I just want to quickly talk about exposure to radioactivity, and then we'll be done with study goal number 39. This was supposed to be in your reading packet. I said it was the last study goal. And a couple of you noticed that it wasn't actually in the reading packet. So I'd like to break down this diagram. I actually think that this is super fascinating. One of the most interesting things in this class. Watch this. All these blues are scaled to all the green stuff, which is scaled to all the red stuff, which is scaled to that yellow thing. Okay. So those blue exposures are measured in units called picosieverts. So technically, remember I told you that all humans are a little bit radioactive. So you get a little bit of radioactivity sleeping next to someone, which is less than, if you live closer, like within 50 miles of a nuclear power plant, which you're going to get more than that by eating one banana, because potassium tends to be more radioactive. Okay, so you put these in perspective, right? Like coal burning power plants are way more radioactive than nuclear power plants because the ashes, x-rays, what happens if you're in a place that has higher background radioactivity, dental x-rays. Can you imagine how many I've had? Here's a normal day. So if you get a dental x-ray, it's like you lived another half day. People who fly internationally get a lot of exposure because long airplane flights put you higher in the atmosphere, so there's more radioactivity from the sun up there. So, every flight across the country is like you're living an extra 4 days of exposure. And, people who do this like twice a week back and forth, people in Hollywood or whatever, when they're 40, they have the cancer incidence of somebody who's 50 from having done all those flights. That's interesting, right? Anyway, you take all that blue stuff, and to put that in perspective, look, we're at 40 picosieverts. A chest x-ray, I've had a bunch of those. That's like 20 picosieverts. Here's the whole blue chart combined, which is, like how much you got if you were in Tokyo after Fukushima Daiichi. If you live in a place that has a lot of stone or concrete, you get 70. There's 3 Mile Island. Here's being at Fukushima Town Hall over the 2 weeks after the accident. This is the limit that you can get, according to the EPA, in 1 year if you're a nuclear power plant worker. So that's like the legal dose limit for a year. Way more than we get in the background. Here's how much you get on average just from potassium. By the way, here's how much you get on average from a mammogram. And whenever you hear that there's a debate about whether or not women should have a mammogram every year or every 2 years, it's about the radioactivity. This is the EPA limit for general people in the public, which is about how much you got if you were near 3 Mile Island during that disaster. That was also how much you would get if you were near Fukushima Daiichi for 2 weeks. If you've had a CT scan, that's double that amount. I've had so many of those. I've broken this, I've broken this, I've broken this, I've broken that. I've had like really bad brain swelling from head injuries. So I've had a bunch of CT scans. Anyway, this is a normal background dose in a year. Most of that is just from stuff that you're exposed to in the environment. Here's what happens if you spend an hour in the Chernobyl plant in the year 2010. Chest CT scans, I've had a bunch of those because I dislocated my shoulder and broke my ribs, and I've had some lung issues. So CT scans. Here's the maximum permitted for radiation workers. So once you're exposed to that much, you have to stop the job for the year. Now, if you take all that stuff, you put it into that box. So there's all the green chart combined. Now this is where things start to get interesting. This is how much we know can clearly increase your risk of cancer. So if you combined all of this, you still have not increased your risk of cancer. All this stuff combined is about 75 microsieverts, and it takes about 100 to start seeing an increase in your cancer risk, okay? But you know, there's a couple of people that were in Fukushima who got almost double that, so they have an increased likelihood of cancer, we think, mathematically. You could take quadruple that and you'll start to have what's called radiation poisoning. Like your body stops working right. There are so many broken chemical bonds that are in so many different parts of your body that some of the systems are going to stop doing what they're supposed to. Severe radiation poisoning is enough to be fatal. So this is how much you would need for that. That's about 20 of this. Oops, sorry. This is what we call fatal radiation poisoning, but you can survive that with treatment. This is the fatal dose without treatment. And get ready now. Emergency workers are usually allowed a small fraction of that. So in an emergency situation, our EPA allows people who have to save property or who have to save lives to be exposed to about 100 microsieverts. So you're allowed to get an increased likelihood of cancer if you're a worker who's saving property, and a little bit more than that, double that, if you're saving lives. But if you put all of that, so here's a fatal dose, 8 sieverts is a fatal dose even with treatment. If you put all that together, here's what happens when you were next to Chernobyl for 10 minutes. We believe that there were doses of about 50 sieverts received by some humans who were right next to the reactor responding to that disaster. The amount of radioactivity that you can get from high-level radioactive waste or from nuclear meltdowns is extreme. It's really, really, really high. I want to emphasize that we really are playing with fire when we play with nuclear power. All the stuff that you could normally be exposed to, even with a lot of medical treatment, even if you're an emergency worker, even if you work with radioactivity, is really, really low compared to the amount that you could get if something goes wrong. I have one more short video to record.